Yeah.
Yeah, so let's see, this workshop was executed on June 16th and 17th, 2 days. And we decided to mold this workshop into the form of a peer Pacific Rim forum. And some of you may remember there's been previous Pacific Rim forums that have been focused on nuclear system safety and the like. And those, in my view, proved to be really effective at attracting an international cohort and an international audience. So we really took this workshop and molded it into the third Pacific Rim Forum. The focus of this workshop was on regional scale simulations of both ground motions and infrastructure response, with a particular focus on performance-based earthquake engineering and how these types of massively parallel simulations in the future might in fact be utilized and impact in a positive way performance-based earthquake engineering. So let me begin by acknowledging the organizing committee and peer. This was a very, very challenging workshop to organize on the web. There were 261 international participants from around the world. There were 41 international speakers from around the world. And so it was quite a logistics effort. And so I just wanted to note the time spent and the effort spent both by the organizing committee as well as Amarnath and peer. And we really couldn't have done it without the dedication of everybody that's on this slide and at peer. So I really wanted to make that point from the start. This workshop was really about taking stock of where we are on the road towards realistic regional scale earthquake simulations. And so, for example, if you think of a region like the San Francisco Bay Area and you have something like the Hayward Fault, one would like to be able to accurately and realistically simulate ground motions throughout that region for a particular fault rupture scenario. And then subsequently, because peer is has such a focus on earthquake engineering and engineering, one would like to be able to understand how those ground motions translate into infrastructure demands and result in the complex and distributed demand on infrastructure throughout that region. And this really kind of goes right to the heart of the lack of strong motion data that I mentioned previously a few minutes ago, and the limitations of such. It would just be wonderful if we got to a state where we could rely on realistic, massively parallel models to generate ground motions that have thousands of spatially dense site-specific ground motions that really can translate that distributed ground motion into an understanding of the distribution of associated infrastructure response. And then perhaps most importantly, allow us to play the what-if game in the virtual space of a computer. To look at multiple earthquake ruptures and see how the distribution of damage varies with earthquake rupture, how to include uncertainties in geologic models and so forth in that rupture scenario. And so one, I think it's not hard to see the potential benefit of a really validated and realistic regional scale simulation model. And we wanted to use the forum to see how far we're along that curve of making such things become reality. And so the forum really focused on the elements of integrated earth science and engineering simulations required to go all the way from the earthquake fault rupture, propagate waves through the earth, and then understand those impinging waves and their influence on a local soil and structural system. And this is a really, really challenging problem for a number of reasons. Number one, it's multi-scale. To capture a large region, it may be on the order of 100 or 200 kilometers or more. And you really want to bring that information down to a local engineered system that may be on the order of 1/100 of a kilometer. So it's truly a multi-scale problem. It's multidisciplinary, obviously, going all the way from geophysics to geotechnical to structural engineering. So that raises challenges. Tends to have coupled linear and nonlinear systems. Soil and superstructures under strong motions can behave nonlinearly. Generally, rock at depth we treat linearly. There's a number of modeling uncertainties, especially associated with subsurface material properties. And then finally, there's just really extreme computational demands in order to be able to do these types of calculations. And so why now? Why at this particular time frame? Well, there's been such advancements in the last decade and a half or 2 decades on some of the underlying physics models for these things like fault rupture scenarios that we're beginning to be able to generate realistic mathematical models of those processes. And then the second thing is, the computational capabilities have increased tremendously by orders of magnitude and continue to increase. And so that's really enabling for the first time these types of calculations to be successfully executed. So I think both of those both of those features contribute to the why now and why this was a timely workshop. We divided the days into very different characteristics. And day one was really to understand the status and where we are in each of the elements of getting from point A to point B. In other words, going all the way from the earthquake source to the end structure. So we subdivided that into a number of sessions, technical sessions. For example, earthquake source representation, geologic models, and how do we generate geological models to support high frequency simulations, nonlinear structural and soil response, geophysics and engineering modeling coupling, and then finally just the computational considerations of these integrated end-to-end simulations in terms of workflow and performance. So day one was really a technical deep dive on all the elements one needs to have. On day two, we shifted gears and we began to think about how do we build confidence in these regional scale simulation models? What metrics and acceptance criteria could we envision for synthetic motions to judge whether they're realistic and representative or not? How do we characterize and propagate uncertainties? And then, of course, verification and validation of simulation results and simulation codes is a challenge in these large-scale models. But all of those ingredients are necessary to build confidence in these methodologies for the profession. Number two, we wanted to have a session on transitioning to practice for performance-based earthquake engineering. How do we think about how these types of synthetic motions and infrastructure response will ultimately be used? And what is the right of phased approach to implementation into practice? And so we had a session on that. And then finally, we talked a little bit about operational models for broadening community access. How do we move these things out of the hands of a relatively small number of researchers in the R&D community and allow them to have access to the broad community, the practicing community, and thereby provide a feedback loop for these motions. So all of these things were foci of the discussions. And so I'll talk about where you can learn about those things in a moment. But one of the things we wanted to do is come out of the forum with some firm follow-on actions and some actionable things, not just have the forum occur and then everybody scatter and then sort of the end of the story. And so we did a couple of things. Number one, as Ramin mentioned in the previous one, we took a lot of polls of the audience. When you have 261 experts at your disposal, you want to kind of tap into that. So we had a number of key questions. For example, this is one of the poll questions. What would be most helpful in promoting and utilizing of simulated ground motions in your research or your professional practice? And we got the poll from all of those, the results from all of those attendees. And interestingly enough, I show the top three answers. Availability of a database of synthetic motions with open access. I'll speak to that more in a moment. Engineering design code guidance for utilization of synthetic motions. It's got to be codified for practice. And then number three, development of rigorous acceptance criteria for synthetic ground motions. How do we judge? How does the practitioner judge if they're not intimately involved in the generation of those motions, whether they're realistic or not? So those are all really good answers and important. So in terms of post-forum actions that we've identified, we're engaging with peer to identify a pilot project for including synthetic ground motions in the peer database as an example. And the notion is a four-step process. We generate large synthetic motions, for example, in the San Francisco Bay Area as an example, and generate those synthetic records for large earthquakes using supercomputers. Number two, we invoke a acceptance criteria for deciding whether those elements are representative. And peer has a leg up on this through some work that they have been funding with Florina Petrona and Norm Abramson, looking at evaluating synthetic motions. And so they're developing a acceptance criteria that would give some insight into the realism of those motions. Number three, probably to get the most engineering utility out of these, you want to store these differently than you've done historical ground motion records. And you want to store a volume of these motions so you can use them in different ways. And so there's been some software developed by the US Department of Energy that will allow you to compress and store a near surface volume of these motions for subsequent use by engineers. And then finally, provide the ability to fetch these motions, either the surface motions or 3D volumes of these motions, so you can utilize that in various manners of code coupling. And for example, using the domain reduction method, if you want fully coupled complex incident motions. So this is an activity that we're in discussion at peer about as a demonstration. And then secondly, I think an important thing, and I'll end with this, is post-forum action is developing a Lifelines working group that would really focus on synthetic ground motions for performance-based engineering. It would answer a number of questions. Number one, and I think this one's really important, establish a clear picture of what constitutes success for utilization of synthetic ground motions and performance-based earthquake engineering, and how do we measure progress in getting towards that goal. Number two, develop a plan for characterization of uncertainty. That's going to be crucially important. Identify early compelling cases to evaluate performance-based earthquake engineering utility, and that would be along the vein of trying to identify some early successes for synthetic ground motions. Provide accessibility and appropriately vetted synthetic motions. And I spoke to that on the previous slide, and that's obviously to the audience and to the organizers, that's a very important thing. And then finally, how do we communicate the status of synthetic ground motions for the earthquake engineering community and to the broad group of stakeholders when they may not have great familiarity with how these motions are generated in the underlying models? That is a really important element of confidence building in our view. So this working group is coming. And so with that, I think I'm about out of time. I'll just mention the forum presentations are all on YouTube, and that's the link. And there's a folder, Peer Pacific Rim Forum in 2021. And so you can jump onto YouTube and you can go through the full breadth of all the presentations that occurred at the forum if you couldn't make it and have interest. And so I think Amarnath, with that whirlwind